Hello everybody, and welcome to our fourth lecture on projections and datums. So far we've covered projections, what they are, and why you choose one over the other. We've talked about datums and geographic coordinate systems. So now let's talk about how to actually use these things in ArcGIS. So start off, how do we work with projections in ArcGIS? And there's two scenarios in which this question comes into play. First, just when you're viewing data, we choose a projection that lets us create nice-looking and convincing maps. Now, another scenario is when we're analyzing the data. In this case, we care more about a projection that lets us calculate accurate measures. Now, we have some important points here to consider. First off, all spatial data are in some coordinate system. Second, all maps are in some coordinate system. And a neat thing about ArcGIS is that these coordinate systems do not have to be the same. So here's a typical scenario. We have data here in 4 different coordinate systems. We have fire severity that's in UTM zone 12. We have roads and state boundaries that are in lat-long coordinates. We've got this background imagery that's in what we call Webb Mercator coordinates, and we have rivers in latitude-longitude coordinates. And ArcGIS can show them to you all together, which is really pretty cool. Understand that the fact that these are in different coordinate systems means that if you picked those things apart and looked at each individual vertex, looked at the coordinates of each vertex, the rivers and the roads, since they're in latitude-longitude, they'd all have a x value of about negative 109 and a y value of around 34. The fire severity, that's in UTM zone 12, that means their x values would be around 650,000, the y around 3.7 million. Then the Webb Mercator data, that background imagery, their x value is roughly 12 million, while their y value is around 3.7 million. So these are radically different coordinate systems, and yet ArcMap is able to bring them all together and show them on top of each other. This is pretty neat. GIS systems didn't used to be able to do this. Now, how do you know what coordinate system your data are in? You can find it pretty easily. If you have it loaded into ArcMap, you can just look at the layer properties. So we can get to the layer properties by either right-clicking on the layer, going to Properties, or we can also just double-click on the layer, a little shortcut to get to the properties. Now here we go. We've opened up the properties, go to the Source tab, and just scroll down in this little box, and it'll tell you the coordinate system. Couple things to notice here. First off, it says projected coordinate system. That's your first clue that these data are projected and are not just sitting in latitude-longitude coordinates. Now also remember that all projected coordinate systems are projected from a geographic coordinate system. So you would like to know what geographic coordinate system it comes from. And you can find that down below. Just keep on scrolling down. Here is the geographic coordinate system that projected coordinate system comes from. Now, so we see that the fire boundary is in UTM zone 12 coordinates projected from the NAD, the North American Datum 1983. Well, what about this other one? What's a Wallow Hillshade in? We can double click on that, open up the properties, the Source tab, scroll down. This is also in UTM zone 12, so those are both in the same coordinate system. And how about these roads? What coordinate system are these local roads in? Double click, open up the layer properties. See that the roads are actually in a geographic coordinate system, WGS 1984. There is no mention here of a projected coordinate system. So that's how you know that these roads are just purely in degrees, or purely in lat-long coordinates. Now notice that we have 3 different maps in this ArcMap document, and you can tell at least 2 of them are in different coordinate systems. So this map, this data frame here, and this data frame here are obviously in different projected coordinate systems. You can tell just because Arizona and New Mexico look different. Now this is pretty common. You often have a little inset map that helps you sort of place yourself on the overall landscape, help people know where they are, and usually you pick a coordinate system that just looks good for that. So what coordinate systems are our data frames in? We get that in the data frame properties. So here's the Wall of Fire, the primary map. We open up the data frame properties, go to coordinate system. We see that Wall of Fire is also in UTM zone 12, projected from NAD 83. How about this this small scale map here, the United States? What coordinate system is that in? That is in USA contiguous Albers equal area conic. So easy enough to find. And notice that it's easy to change them here as well. So if we wanted to project this in a different coordinate system, sinusoidal's a good one for equal area analysis. We can pick this, hit apply, and it reprojects itself into the sinusoidal. Sinusoidal is good for equal area, but boy, it can twist and warp the polygons quite a bit. So that's how you figure out what coordinate system your map is in and how you set it. Now remember, as you change these coordinate systems, this only really applies to how you view the data. This is not affecting your analysis at all. But you do have an awful lot of choice when it comes to what coordinate system you want to view it in. Let's look at some examples. And by the way, what coordinate system do you suppose a map is in before you load any data into it? So here we have a blank ArcMap document, nothing is in it. Well, we have our data frame. What is the coordinate system? It starts out with no coordinate system. Right now it just assumes nothing about your data. This is actually different than ArcGIS Pro. ArcGIS Pro will always load in some coordinate system into the map. ArcMap lets you start without a coordinate system, and this can be useful when you have data that don't fit into a global system. Maybe it's a local coordinate system. And let me just explain what I mean by that. We're not going to use local coordinate systems in this class, but they do exist, especially in engineering projects. Maybe you're going to put in a housing development or build some structure somewhere, and you'll start with some control point. This will be your 0 point. You pound a stake in the ground. This is where everything is measured from. And then 10 meters north of that, you'll put a wall. And 20 meters north of that, you'll put a door. So the wall's coordinates are based out from that central control point. They're not referenced to the globe as a whole. They're not. There's no connection to any latitude-longitude system. It's purely a local system. Like I said, you see this kind of thing a lot in engineering projects, and not so much in land management or ecological research. Anyway, right now we have no coordinate system. Notice what happens when we add the first data set, though. I'm going to add the National Geographic map. Here we have it. We check the data frame coordinate system again, and notice it has set the coordinate system to be equal to the first data set that you added. Now later on we can change it, of course. Notice that this data set is in WGS 84 Web Mercator Auxiliary Sphere. This is projected from the GCS WGS 1984 Geographic Coordinate System. All right. So we want to talk about all the options we have for coordinate systems. If you look in the geographic coordinate systems, you see all these different options. These are all the different lat-long variations you have available to you. You can also set your map to be in any projected coordinate system. It does not have to be in the coordinate system of that data set that we just added. Earlier I showed you sinusoidal. We can do that again. See what the globe looks like in the sinusoidal coordinate system. So we've changed our data frame coordinate system that easy. Now there's lots of these that are kind of fun to play with. I really like one called the world from space. I think I mentioned that before. And remember, this is the orthographic projection. It even says it's orthographic here. We just hit apply. We're going to discuss this warning here shortly. Okay, the world from space. Zoom to the full extent. And that's how easy it is to choose from the set of coordinate systems that are available to you. Inevitably, you are going to double-click on one of these and open up the properties for that coordinate system, and that's fine. This lets you change how that coordinate system is set up. Basically changes where the projection surface intersects the planet. Now in this case, the default orthographic for some reason is set to be negative 72 degrees longitude, 42 degrees latitude. Looks like it's centered roughly on New York City. We can change this to Flagstaff, negative 115, latitude of about 35. Hit apply, and it rotates it to be centered on Flagstaff. So any of these coordinate systems can be modified. and it's fairly easy to do. And you might notice as you're searching through the coordinate systems, trying to pick the one you're going to settle on, if you start looking through them, you might notice that several of them have things like equal area in the name, conformal in the name. Here's an equidistant in the name. So you kind of get a clue on what the purpose of it is. So an equidistant, we could choose this if we're wanting to do true distances. The conformal will probably look best. Equal areas are better for analyzing sizes. And another neat feature is, suppose you want to set the coordinate system of your map to be equal to one of the coordinate systems of the data that you have in that map. So, for example, suppose I have the National Geographic map here, and we remember that was in the Web Mercator coordinate system. There's actually an easy way to set ArcMap to be equal to Web Mercator when you have a layer that has the data in Web Mercator or any coordinate system. What you do is you go into the Layers option. This will show you all the coordinate systems that are currently available amongst all the data sets that are currently loaded in your map. Right now we only have one layer, and we happen to know it's Web Mercator. We can click this little plus box here, and it'll tell us all the data sets in our map that are in this coordinate system. So if we had 6 or 7 of them here, and they're all in Web Mercator, we'd see Web Mercator here, and then 6 or 7 layers listed beneath it. But in the meantime, if I want to go with Web Mercator, all I have to do is select it here, hit OK, and it switches me back to Web Mercator. Okay, as we've been seeing, ArcGIS and ArcMap does a great job at switching around between projected coordinate systems. It's actually pretty easy. It's a simple mathematical transformation. ArcGIS will do it automatically for you in your map. And ArcGIS provides several easy tools to reproject data layers into new projections. So, for example, if your data are in geographic coordinates, they can easily be shown on a map in UTM coordinates. All of this works really well. Now, surprisingly, switching around between different geographic coordinate systems is much more complicated. So suppose we want to project our data into a new projected coordinate system that's based on a different underlying geographic coordinate system. And let's just be clear on what this means. When we're transforming from one geographic coordinate system to another, we're moving from one datum to another. We're changing spheroids. We're changing the underlying model for the shape of the Earth. So it's fairly complicated to figure out how to move the coordinate from one of these models of the planet to another. But that's what it means to change a geographic coordinate system. And for example, we have data that's in UTM Zone 12, but that's projected out from the NAD 1927 datum, and we want to project it into UTM Zone 12 based on the WGS 84 datum. So they're both the same projection, and they're both projecting into the same projected coordinate system, but they're projecting out from 2 different underlying geographic coordinate systems. This causes ArcGIS trouble. Another scenario is when you want to add new data to your map, but your map might be set to something like WGS 84 or any projection that is projected out from WGS 84, and you add data that comes from NAD 83. Well, you're dealing with a conflicting geographic coordinate system, and again, ArcGIS has trouble with this. Turns out there's no single simple mathematical transformation, therefore ArcGIS does not do it automatically. This is different than the projections. Remember, ArcGIS handles projection changes just fine. It's these underlying geographic coordinate systems that give it grief. So the issue is that ArcGIS actually has many possible transformations that you can choose from, and each option is designed to work better in a particular area. So, for example, if you want to convert between NAD 83 and WGS 84, there might be a dozen different methods that ArcGIS knows about, and ArcGIS needs you to tell it which one to pick. Now, as of ArcGIS 10.1, ArcGIS does try to help. It tries to pick the best possible transformation for you. When it shows you the list of options, it'll pop its recommendation up to the top. This is easy to fool, unfortunately, but it's still a lot better than it used to be. Esri does provide this document, Geographic Transformations PDF, to help. And a lot of people don't even know it exists, so I'm going to show it to you. It comes with your installation of ArcGIS, but I've also added this document to your Documents folder. Now, if all else fails, you can make your own transformation. You can set up the rules to convert between two different geographic coordinate systems, but this requires a pretty solid understanding of the mathematical functions that are going on, and that's not that easy. So hopefully you never have to deal with this. Or if you do, it's because you want to and you're just having fun with it. Now, I want you to get used to these warning messages. These are what we've been seeing quite often as we've gone through this class. These are warning messages to you to let you know that you are dealing with conflicting geographic coordinate systems. You may have two different data layers in your map that come from different underlying geographic coordinate systems, or you might just have your map itself that's based on some geographic coordinate system and you're adding data that comes from a different one. In either case, ArcMap is having to deal with conflicting geographic coordinate systems, and it needs your help to pick the right method to transform between them. Now, for example, here we have a scenario. Your map is in UTM Zone 12, and this UTM Zone 12 is projected out from the NAD 83, the North American Datum 1983 geographic coordinate system. Now you have data that's also in UTM Zone 12, but your data is projected from the North American Datum 1927 geographic coordinate system. So you need to tell ArcGIS which of several possible methods to use to convert between NAD 27 and NAD 83. And there's usually several options to choose from. It's not always easy to know which is the best option. And like I said, each option works better in some particular region. So here's how you do it. Okay, here we have a map of the Flagstaff area. We have one layer in the map, this National Geographic World Map. Let's take a look. It is in Web Mercator coordinates projected from WGS 1984. So it's based on the WGS 1984 geographic coordinate system. The map itself is in the UTM Zone 12 coordinates projected from NAD 1983, so we're already dealing with two different geographic coordinate systems. Now, how do I make these two geographic coordinate systems line up? Well, I hit the Transformations button, and it opens up this little window that takes a little practice to understand. So let's look at each part of it. First off, we have Convert From, and then we have one or more coordinate systems listed in this box. Then we have Into, and then right now it says GCS North America 1983. That's the same as NAD 83. So what's happening here is this Into is telling us that the map itself is in this coordinate system. And understand it's not necessarily in this geographic coordinate system. It's either in this geographic coordinate system or it is in a projected coordinate system that is projected from it. Regardless, the underlying geographic coordinate system of this map is North American Datum of 1983. Up here we see that there is something in the map that is coming from WGS 84, and so we're going to use this window here to tell ArcMap how to transform between WGS 84 and NAD 83. We click the little down arrow here and it shows us the options. These are all the ways that ArcMap knows how to transform between WGS 84 and NAD 83. So it's up to you to pick the right one. As of ArcMap 10.1, Esri did make this a little bit easier. It used to be that they would list these in alphabetical order and we had to pick one, and that was just ridiculous. Now they have sorted them in order of appropriateness to your location. So right now it's assuming that we're in the Flagstaff area, I hope, and it is picking this option because that is most appropriate for the Flagstaff area. Now this option would be more appropriate for somewhere else, and etc. This one apparently is designed for Montana and Idaho, so wouldn't be so good for Flagstaff. But anyway, this is rising to the top of the list, so we would generally go with this first one. Now, not always, and I'm going to show you how to look these things up, but we can often rely on this to be the, most accurate. So I have now picked this transformation which is designed to transform between WGS84 and NAD83. And when I set this, I will hit OK, and now the map will correctly line up between WGS84 and NAD83. Now I'm going to add the Coconino National Forest, just so I have the boundary here. The Coconino National Forest boundary is in UTM Zone 12, projected from WGS84. This is the WGS84 is what matters when we're concerned about geographic transformations. So we have data in WGS84, but we already have the transformation set so that ArcMap knows how we want to transform between WGS84 and NAD83. Okay, let's add another data set. I know I have some data up here from NAD27. Happen to have an old fire boundary that is I know it's in NAD27 coordinates. So I add that in, I see this warning message. This is telling me that I'm adding data in a geographic coordinate system that is different than the map. Notice it gives you options not to warn you again. You may or may not want to turn this off. If you've got your ArcMap session fixed up so it's doing the correct transformations, then you might choose this option. But never choose this option. Never choose the one that says, don't warn me again ever. We want to know when this is happening. And if we turn this off, then we'll never find out when it happens. And that's a bad deal. All right, so this tool will let us get right to the transformations window. And we can set up our new transformation. Now, notice what we got going up here. This is the same window we saw before. It's showing us all the geographic coordinate systems that are currently at play in your map. Notice it's not showing you any projected coordinate systems. Whether or not the data is projected is irrelevant to this whole question of geographic transformations. We don't care about the projection when we're worried about lining up underlying geographic coordinate systems. So no list of projections here, but we do have 3 geographic coordinate systems at play, and the map itself is still in NAD83. So earlier we set the transformation that would convert between WGS84 and NAD83. See, it's still set down here, but we haven't set anything for NAD27 to NAD83. So now we can set that. We'll click here. This is the list of options that ArcMap knows about. It's recommending this one at the top, and that is a pretty good one. So we'll go with that. Hit OK, and now close. All right, so now we have data from 3 different underlying geographic coordinate systems, and ArcMap is lining them all up correctly. We can open up the transformations window again right from the data frame properties, and we can confirm that we have all those things set. So NAD27 to NAD83, we're using this transformation. From WGS84 to NAD83, we're using this transformation. Now there is this third one, converting NAD83 to NAD83. Well, they're the same thing, so there's no point, right? All right. And that's all there is to it. All you have to do is remember to set this value, and as long as you choose a reasonable transformation, then from here on out your data will line up correctly. Okay, now a couple more quick points on these transformations. Esri gives you all these transformations to choose from, and it's kind of up to you to pick the one that you think is appropriate. It's nice that they put one at the top, and that does help. But suppose you do want to look them up. You're not sure that the one that they selected is best. And really think about this. How does Esri determine that one is best? It's got to be based on your current location, but how does it really know what your current location is? It can make a guess based on where you're zoomed into, or based on the data sets you have loaded. But sometimes you have global data sets and you're zoomed to the world. And so how will Esri know then that you need the transformation that's appropriate for Flagstaff? I actually asked the person in charge of these projections and datums at Esri one time, and she told me that they do have an algorithm, but the algorithm is, quote, easy to fool. So don't rely on it. Sometimes you want to look them up and see which one might be appropriate, and so this is how you do it. You go find this document called Geographic Transformations 10.1.pdf, and right now it's in your Documents folder, but it's also installed when you install Arc. It looks like this. Notice that if you remember in our previous demonstration, ArcMap suggested this particular transformation to transform between WGS84 and NAD83. Well, we can look it up, and we can see that this particular one is designed for the USA, all states, and it's appropriate between these particular latitude and longitudinal ranges. So if we want to look up any of the others, we just search for the name of that transformation, find it in this document, and see where it's appropriate for. Now there's a new thing that came out, well, new as of 10.1, so I guess it's been a little while, but it is pretty neat. It is the idea of compound transformations. Now this means that you transform in multiple steps. And this is a good idea because if you consider that there's nearly 1,000 different geographic coordinate systems, and if you want to be able to transform from any of those to any of those, well, that's a huge number of permutations. That's just a lot of transformations that you would have to create in order to make all those connections. So the solution is to pick some common transformation. You can transform every one of them into that common transformation. WGS84 might be good. You could take any one of those geographic coordinate systems and transform it to WGS84. Well, that's just an intermediate step. So then you transform again to get to your destination geographic coordinate system. Maybe a two-step process, but by setting up this intermediate stage, you just hugely reduce the total number of transformations that you need to write from scratch. So it's a neat thing. Downside is it makes it a lot harder to look up what's the appropriate transformation when you have to. This NAD27 to WGS84 number 79, and then it transforms there from NAD27 to NAD83 NADCON. Well, you have to look at both of those to see if it's appropriate. And it's tedious, but now you know how to do it, so it's not impossible. Okay, I think that's enough to cover in this video, and in the next video we'll wrap up our discussion of projections and datums by learning about how to actually project your data into new coordinate systems. Now, this means to create brand new data sets in that new coordinate system, and we'll look at why you might want to do that, and the tools available to you, and some special issues with projecting raster data.